One.
Okay. Thank you, David. Thank you to all the organizers. This is my first talk like that, so it's a little bit frustrating, as you probably for everybody of you. But let's try to do some math. And it's also an honor to speak in this conference in memoria to Pera Mumbru, who was a good friend. Okay, so the title is Group and Dynamics. It's maybe a little bit too much. I should have said some group and some dynamics, but okay. So the object I would like to discuss today are groups and dynamics, but very specific groups and very specific dynamics. And my goal is to try to explain the relationship between these two objects. So the group I want to talk about are surface groups. So very simple group in some sense, where the surface are supposed to be closed and compact and of rank larger than 2. In some other sense, they are hyperbolic surfaces. And the map that will occur during that talk are mapped from the circle to the circle that are piecewise homeomorphisms. So piecewise homeomorphism means that the circle admits a partition into finitely many intervals, ij, and the restriction of the map to each of these intervals are homeomorphism onto their image. And we've seen maps like that in yesterday's talks by Adrien Boulanger, who gave, in fact, 2 examples. The first one was the interval exchange maps, where you have intervals and the map restricted to each interval, it's an isometry for some metric, and you just exchange the intervals. The other class he was considering was a fine interval exchange map. So the restriction to each interval was a fine map. So here it's a little bit different. It will be a homeomorphism on each piece, and not any kind of homeomorphism. It will be some expanding homeomorphism. I'll try to explain a little bit. Okay, so now let's talk about the surface side. So the surface group, it's a very classical object, and we can see it from many different point of views. And let me take only 4 different aspects. The first one is the very classical aspect of surface group as discrete subgroup of PSL2R, so 2 by 2 matrices with real coefficients. And it's classical that this acts on the hyperbolic plane H2 and also extend to the boundary. So extend to the boundary means that on the boundary, the group act as a discrete subgroup of the homomorphism of the circle. And we'll see that later. And the third aspect, it's purely combinatorial group theory. So group in this setting is a combinatorial object given by a set of generators and a set of relations. And so this is the kind of approach I will try to use in a combinatorial setting. And also what's special about surface group is that if the rank is large enough, if the surface is hyperbolic, then the group as a group is hyperbolic in the sense of Gromov. And the boundary, as a Gromov boundary, it's a circle. Okay, so let me just discuss some very small backgrounds about action of the group on hyperbolic surfaces. When you have an action which is co-compact and by isometry on the hyperbolic space in general, but in particular on the hyperbolic plane, then you have a fundamental domain which is compact. And this fundamental domain defines a very particular set of generators and relations. And in this class, each generator can be seen as an element of PSL2R, and they are hyperbolic in the sense that they have 2 fixed points at infinity. And each of these generators, alpha j, induces a diffeomorphism on the boundary, a circle, that satisfies some very particular property called Möbius. So in particular, this diffeomorphism on the circle, they are analytic and they admit two fixed points, one attracting and one repelling. And using this classical material, Bowen and series at the end of the 70s, in 1979, they prove a kind of beautiful theorem, which is the following. The theorem said that, so their theorem is a little bit more general than that. They are using not only surface group, but function groups in general. But for surface group, it's just one particular case. So surface group acting on H2. So the theorem said that there exists a particular action called A star, and the associated fundamental domain delta A star satisfy a very special property that they call property star. Whatever that means, I will not explain this property. But from that property and this particular action, they prove that you can associate to this action a very particular map, phi, from the circle to the circle, which satisfies three properties. The first one is that the map is piecewise Möbius. So it's a restriction to each interval, it's Möbius. The map is Markov in the classical sense of dynamical system. And the last property, which is the more surprising, is that the map and the group, remember that the group acts on the circle by homeomorphism. This third property is that the map and the group are orbit equivalent. So I'll explain a little bit more later what this means, but essentially this means that the orbit of the G action and the orbit of the map action are the same. So of course, this is a strong connection between group on one sense and dynamics. So now, as I say, I would like to enter this story from the combinatorial group approach. So a combinatorial group is that you give yourself a group as a presentation, set of generators and set of relations, finite set of generators and finite set of relations. I'm guessing that most of you have seen that, but what a relation, it's a word in the set of generators. And the presentation defines, in fact, two geometrical spaces, very classical also, the Ka graph, and I guess it's so classical that I will not explain, and the Ka2 complex. It is also classical, but maybe less known in the dynamical community. What's the Ka2 complex? So remember the Ka graph, it's the graph where the vertices are the group element, and you have an edge between two elements if they are connected, if these two group elements are connected by a single generator. So it's a graph, and it's a metric space because you could declare that each edge of this graph has length 1. So it's a metric space. So the Ka2 complex, it's the complex that you obtain by gluing to this Ka graph some collection of two cells. And what are the two cells? So if you have a relation in your group, that means that in your Ka graph you have a loop, because the relation tells you that when you follow a path in your Ka graph, you go back from the identity to the identity, or from any vertex to the same vertex, following in the Ka graph your relation. So the Ka2 complex is the complex that you obtain by gluing on the Ka graph. Each time you see a relation as a loop, you glue a two-cell, a disk. So it's a two-dimensional space, which usually for an abstract presentation could be a horrible space. And what's special for surface group is that they have some particular presentation that I'm calling geometric. And a geometric presentation, it's a presentation of the surface group, so that if you consider the Ka2 complex, it's a plane. And in particular, the Ka graph, it's a planar graph. And if you just think about the classical presentation of surface group that you've learned probably at some point, it's very clear that they all are geometric in this sense. So the classical presentation of surface group are geometric. And this is a subclass of all the possible presentation. And now the analog of the theorem by Bowen and series in this setting of combinatorial group is the following. It's been published in 2014, and so you take a group, surface group, and you take a presentation which you assume is geometric. And so the statement that there exists a map that depends on the presentation, phi p from S1 to S1, with essentially the same property that in the Bowen series theorem. A little bit different. The first one is that you cannot expect the map to be Möbius, but the best you could expect is that the map is piecewise homeomorphism. And in this case, it's expanding. I'll explain a little bit what that means. The map is Markov in the classical dynamical sense. The map and the group, the action of the group on the circle, are orbit equivalent. And the fourth property that is surprisingly Bowen didn't see is that the topological entropy of that map, this is one dynamical system, you can compute the topological entropy, equals the volume entropy of the presentation. So I'll explain a little bit what's the volume entropy, but this is very similar to the topological entropy. So in addition to that, the map in question, this map phi p, is completely explicit once you have the presentation. So in other words, you can compute the map and you can compute the entropy of the map because it's a Markov map. And therefore, the volume entropy is computable, which is not that so often in the group category. Okay, so my goal is to try to explain a little bit what behind that construction, the construction of that map. So some explanation about the statement. So expanding piecewise homeomorphism. So piecewise homeomorphism, as I said in the beginning, so it's a homeomorph. It's the circle admits a partition, and the restriction of the map to each of this interval, it's a homeomorphism onto its image, and it's expanding in the topological sense. If you have, in addition, a metric on that circle, then you could say, okay, the map is expanding in a metric sense. If you don't have a metric, it only say that it's expanding in a topological sense, mean that if you take collection of sequence of pre-images, it shrinks to a point. An observation about this map that they are not continuous. You have points where the map is not continuous. They are surjective, but not injective. So the Markov property is the classical one in dynamical system. And so I will not explain because I guess most of the people in the audience knows. So the orbit equivalence in this setting is maybe less classical. So saying that a map and the group are orbit equivalent if they act on the same space, here the circle, say that if you have 2 points in the same orbit of the group, meaning that there exists a group element J that send one point to the other, U equal G of V, if and only if they are in the same orbit under the map, which means, and remember the map is not invertible, so we can only iterate in the positive direction. So which means that you have two integers, positive integer, n and m, so that the nth iterate of U equals the nth iterate of V. And this is up to finitely many possible exceptions. So I guess the topological entropy is also a classical invariant dynamic, so I will not explain. The volume entropy, it's very similar quantity. So I'll explain with my hair. So the idea is that you have the group, the presentation, and the Ka graph. I told you that the Ka graph is a metric space. So if you have a metric, you can look at balls. So assume you take a ball of radius r, and the vertices are the group element in the Ka graph. So you count how many group elements are in the ball of radius r. Classically, this number will grow exponentially. So you take the logarithm, divide by the radius, and you take the limit when the radius goes to infinity, and you have a number. This number exists by subadditivity property. And this number is called the volume entropy of the presentation. This is not a group invariant. This is an invariant of the presentation. And okay, so now let me try to give you some idea of the construction from a presentation of this collection of maps. So again, the idea is to play with the presentation via the Ka graph and the space at infinity. The space at infinity, it's a circle. So now this definition is valid for any hyperbolic group, and we will use it for the surface group and the circle for the boundary. So take a hyperbolic group with a generating set Y. What I want to define, it's a subset of the boundary that I call cylinder set, and you will see that there is some analogy with the cylinder set in combinatorial dynamics. Okay, so the boundary of the group is d gamma, and then we fix one generator in the generating set Y, and the cylinder set is the set of points on the boundary, so the point at infinity, so that there exists one geodesic ray writing of that point. So there is a geodesic ray starting at the identity, converging to that point, and precisely that start at the identity by the letter Y. And so this is very reminiscent to the cylinder set in combinatorial dynamics. In combinatorial dynamics, the cylinder set is just a subset of the set of infinite words that start with a fixed beginning. So here, the beginning is just one letter, one generator, and the geodesic ray, it's an infinite word in the Ka2 graph. And the difference between the combinatorial dynamics, the symbolic dynamics, and the group setting, that usually there are many, many words, infinite words, that arrive, converge to a given point on the boundary. So that's why this definition here is say that there exists at least one of these infinite writings that start with a given letter. So for a general hyperbolic group, these cylinder sets are probably horrible sets. I have no idea what are the topology of these sets. And in addition, they are horrible sets, and they depend on the presentation, which is not a good news in group theory. What is a good news is that for this very special surface group and very special presentation, the geometric presentation, we have this lemma that tells you that for geometric presentation of a surface group, if you take any generator, then the cylinder set, Cx, is a connected set. In other words, it's an interval. And in addition, if you take two cylinder sets, they intersect, but they intersect if and only if they are adjacent generators. So X and Y are two generators in the generating set capital X. So they are adjacent, mean that, remember that the Ka2 graph is planar. That means it is embedded in the plane. And so from that specific embedding in a plane, you obtain a cyclic ordering of the edges that start from the identity, or the edge that start at any vertex. And this cyclic ordering induces the cyclic ordering of the generators. And in this case, if these two cylinder sets intersect, they intersect in a non-trivial way, meaning they intersect in an interval. Okay, so now I will give some notations. Since we have a cyclic ordering of the generators, I will label the generators according to this cyclic ordering, x1 up to x2n. And I will call Gi this interval corresponding to the intersection of two cylinder sets. Okay, so that's the basic object. And now it's a construction and it's a definition of a family of maps. I will not define one map, but I will define a family of maps. Again, we consider a geometric presentation of a surface group with two n generators. We fix an orientation of the circle. And on that circle, we fix a collection of two endpoints that I call θ1, θ2n, where each θi belongs to this interval Gi here, the intersection of two cylinders. Okay, and now we have one point for each of these interval Gi, and therefore we can define intervals in between these 2 points. So if you take 2 points, 2 consecutive points in this circle, let's call it theta I, theta j, and theta j plus 1. The interval in between these 2 points is called ij. And you observe that by definition of the cylinder set, this interval is a subset of a cylinder set Cxj. Okay. So now here it's a definition of a family of maps. You fix this collection of points, theta, and then you define a map from the circle to the circle as follows. You take one point z on a circle. This point has to belong to one of this interval ij. And to this point, you act by the generator xj minus 1. Remember that xj, the generator of the group, they act on the circle, and here the circle has to be understood as the boundary of the group, which is a circle, acts on the circle by homeomorphism. So which means that here you have an action on the interval ij by the homeomorphism xj inverse. So this is the notation xj inverse of z, mean that this is the action by the homomorphism. And the map, as I said, it's a piecewise homeomorphism because on each interval ij, the map is a homeomorphism. And this is not one map, it's a family of maps because the parameters are the point theta that I choose in each interval gi. And for just terminology, these points are called the cutting points. And now if you look at the history of that map, if you the map that Bowen and Series and Bowen alone have defined for the very particular presentation that they obtained from the particular action that they got, it's a map in this class for, again, a very particular choice of the cutting points. And this choice comes from the geometry of the action. Also, the map that I constructed in my paper was also of that type, for this time for all geometry presentations, and for a canonical choice of the cutting points, namely some kind of combinatorial notion of a midpoint of each of this interval gi. Now, the observation that makes this map kind of very particular is that in some sense, there are shift maps. There are some group version of shift maps. And let me explain why there are shift maps. The reason is that if you have a point in an interval ij, remember that this interval ij is a subset of the cylinder set Cxj, which means that there exists a geodesic ray starting from the identity by the letter xj. So this is this writing here. There is a writing of z as a geodesic ray that starts by the letter xj and is followed by some infinite word w, which has to be a geodesic ray. So in particular, w is it's a geodesic also. And now the map is applying xj minus 1 to this point. If you apply that and you compute, you observe that the action of this map on this particular point is just shifting by removing the first letter xj. In other words, phi, one writing of this image is just the infinite word w, which is another point on the boundary. And for that particular writing, it's a shift map. So here it's a, let's say, the simplest example. The surface, it's a surface of genus 2. I'm sure you've seen surface of genus 2, and this is the very, very classical presentation. So you have 4 generators, and the inverse, you have 8 generators, and you have one relation, which is a product AB, A inverse, B inverse, CD, C inverse, D inverse. So it's one word. And the expert will recognize that this word is particular. This is a product of commutator, but whatever, this is one word. And since it's a classical presentation, this presentation is geometric, as I said in the beginning. And this picture, it's a very small part of the Cayley graph around the identity. So this vertex here, it's the identity. From the identity, you have all the generators, A, B, and so on. This cyclic ordering is reflected by the relation, and it's well in the plane. And this loop that you can see here is precisely the relation, A, B, A inverse, B inverse, and so on and so forth. Okay, so what you see from that picture, you see that if you start at the identity by the letter A, what you have after A is all this possibility, all the other letter except A inverse. And this line here that you can imagine go to infinity are one possible choice of the cutting point if you believe this line go to infinity. So this line going up to infinity define one point on the boundary here and one point on the boundary here. And the interval at infinity on the circle in between these two lines, it's the interval that with this notation here would be IA. And why this map is expanding, you see, when you have this interval IA, so here it's the interval IA, the image of IA is everything that can be after A in an infinite writing. So if you look at this picture, you see that you can have anything from B inverse to blah, 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 up to B, which means that the image of an interval, it's an interval that starts here in the interval IB inverse, and that end here in the interval IB. So as you can see, this is very, very expanding as a map. Okay, so now are some questions, and I will not answer all of this question, but let me give you some directions for the question. So the first question is, are these maps in this family really different maps? In other words, do they have very different dynamics? The second question, which could be strange from that perspective, that is the topological entropy an invariant of that family? In other words, is it a constant topological entropy for all map in that family? Another class of question is, how particular are the map in this family phi theta among all the possible expanding piecewise homeomorphisms on the circle? Is it a big class or small class? Can we characterize them? And here is my favorite question, which is, I would call that a conjecture. You see, we made a connection between volume entropy and topological entropy. And as many of you probably know, when you have topological entropy in a class, it's natural to look at the minimal topological entropy on that class. And usually the minimal topological entropy should have some very strong properties. So if the minimal entropy is realized, so the map that's realized, so this minimal, need to have some very strong property. So here's the essence of that conjecture. There is one natural candidate to be a presentation with the minimal volume entropy. And this natural candidate is the classical presentation for surface group, which in terms of generators and relation means that you have a presentation that would be geometric and with the minimal number of generators. And here the question is phrased like, is there a best possible presentation, in a sense that, is there a presentation with the minimal volume entropy among all possible presentations? And I'm very, very far from having an answer to that question. So let me discuss a little bit these four questions. So the first one is, does the different maps in that family really different? And the answer is yes, they are very different. And in particular, they are usually not conjugated, they are even not semi-conjugated. You remember that in the Bowen-Serid theorem and in my theorem, there was a statement that there exists a map that was Markov. And among all this map in that family, there are many of them are Markov. In fact, there are a countable choice of the cutting point theta for which the map is Markov. But for most of the choices, the map is not Markov. And that's another question. The best we could expect from different maps in this family is they could be orbit equivalent. And this is an open question. We have some reason to think that at least for some sub-collection, they are orbit equivalent, but I don't know whether this is always the case. The second question was about the topological entropy. The question was, is it possible that the entropy, the topological entropy of all the map in that family is constant? And if it's constant, it has to be the volume entropy of the group presentation. And the reason why this question makes sense is that first, it's not obvious because, as I say in the point number 1, these maps are not conjugated, but they could be different. And on other direction, for the map that are Markov in that family, they have the same entropy, and the entropy is the volume entropy by exactly the argument I use in my construction to prove that the volume entropy equals the topological entropy of the specific map I constructed. And so in general, we have not yet an answer, but there are some work in progress on that question with Frances Magnosa, David Juher, and with Alceda. And the current belief that the answer should be yes. But up to now, we only have very partial answer. And the best we could have right now is that the answer could be yes for a full subset, for a subset of full Lebesgue measure. And actually, if you think about that, it's a kind of surprising family, because usually in dynamical system, when you have family of dynamical system with positive entropy, usually the entropy is very sensitive to the change of parameters. So what makes this family quite special is precisely the fact that it comes from a group action. And that probably because of the group action that make the constraint that the entropy could possibly be constant. Okay, let me turn to the third question. The third question was, are this map coming from a group presentation very particular among the piecewise homomorphism on the circle? So there is only a partial result on that question. This is a work in common with Natalia Viana-Bedoya in San Carlos. And this is a geometrization question. The question more precisely is the following. You give yourself a map, which is a piecewise homomorphism on a circle, with nice enough properties, and that's the problem. Find some nice enough property in order to get the result. And the result would be, from that map, can you construct a group from the map and prove that the group is in fact a surface group, and that the map you started with is a Bowen series-like map for that group. And this is why I call this a geometrization question, because you start from the map and you get a geometry. The geometry is a group action. And what we did with Natalia Viana-Bedoya was to identify some quite nice dynamical properties for some map in the class that, for this subclass, allow to construct a group and a group action on a hyperbolic space. And then from this action, we could prove that the group, in fact, is a surface group, and the map, in fact, it's a Bowen series-like map for that group. So this paper is not yet published, but I hope it will. And I will not explain the dynamical property that we found, but there are essentially three classes of property. The first one is that we assume that the map is expanding, but expanding in a very strong sense, exactly like in this picture. This picture shows you that the image of one interval intersects all other intervals except one. And the one that is not intersected is exactly correspond to the inverse of the generator associated to the first interval. So this is the first part of the property. We need to assume that the map is really extremely expanding. The second class of property that we use is, again, we can see that on that picture. You see, from this picture, we see that the interval that is on the boundary, on the circle here, the point that corresponds to this limit here, which is the cutting point, has two sides. One side belongs to the interval IA, and the other side belongs to the interval ID. So which means that this point has two orbits, one from the left and one from the right. There are many situations in dynamical system when you have the discontinuous map and orbit from the left and the right, and the orbit has nothing to do in common. So the property that we can see from that picture is that, remember that the map is a shift map. So shift by the letter A, and then the letter B, and then the letter, and so on and so forth. So which means that we can see that the map need to have some special property around the cutting point. And the special property is that there should be some iterate, let's call it K, so that the iterate from the left and the iterate from the right, for the same iterate K, are the same point. So this is a property that we call the eventual coincidence property, which seems to have some independent interest. And the last property that we obtain is what we say, it's the map is conjugated to a piecewise affine map on each interval, with the fact that for each interval, the slope is constant, is the same, some number lambda. So which is a very particular property. And in fact, this is not surprising to have such a property if the map is Markov. If the map is Markov and expanding, then we know from Piron-Frobenius that you can change the metric on the partition interval of the Markov partition, so that the action of the map is just multiplying by some number lambda, which is the largest eigenvalue of the Markov matrix. So this is not so much of a surprise that such maps could be conjugated to a map that is everywhere affine, and the slope is the same lambda everywhere. Okay, so now I'm almost at the end of this talk, and the last question is about the minimal entropy. And as I said, this is completely wide open question. The question being, can you find a presentation with the absolute minimum volume entropy among all presentations? The only partial result that we have on that question is the fact that among the geometric presentation, we can use this dynamical system approach. And among this geometrical presentation, it's not that difficult to check that the presentation with the minimal number of generators have the minimal entropy. And this gives the answer, but only among the geometric presentation. Okay, so I guess I was a little bit fast, and my talk is finished now. Thank you.
Okay, thank you very much, Jérôme. So it's time for questions, comments, remarks.